Welcome to this video lesson, which is the full solution to the practice questions from lesson 20, which focuses on the distance between a point and a plane. For the first question here, we are to determine the foot of the normal and the shortest distance for these two situations where we got a point and we got a plane. For the first one, let's draw out the situation. We got a plane, let's say this is x minus y plus 3z is equal to negative 10, and let's say this is our point Q, which is 2, negative 1, and 3. It's going to meet this at a point. Let's call this point X, Y, and Z. And basically the equation of the plane that's given to us is giving us the normal of this planes, and the normal of this plane is in the same direction as our line there. So because we know that this is perpendicular and the normal is also perpendicular, so the direction of our line there is going to be the coefficient of x, which is 1, coefficient of y, which is negative 1, and coefficient of z, which is 3. Once we have this, we can write an equation that goes through points Q and P. We have a point and we have a direction vector as well. So our points, so the line there is going to have an equation R is equal to a point, which is point Q, 2, negative 1, and 3, plus our direction, which is 1, negative 1, 3 times some sort of parameter. In this case, we're going to use the letter t. Once we have this equation for the line, I'm just going to rewrite it in forms of a parametric equation. It's a little bit easier to use this, and you don't have to write it if you're much more comfortable. You can just use the vector equation, but I've just rewrote this equation using the x component, the y component, and the z component. And once I have the equation of the line, I'm going to use the equation of the plane to figure out what is the t value for which the line touches the plane here. So what I will be using is I'm going to plug in the x value here, the y value here, and a z value here. X is 2 plus t minus y, which is negative 1 minus t, plus 3 times z, which is 3 plus 3t, and that's going to equal to negative 10. Then I will expand. I will get negative 1 times negative 1 is positive 1, negative 1 times negative t is positive t, plus 3 times 3 is 9, and 3 times 3t is 9t. That's going to equal to negative 10. 2 plus 1 plus 9 here is 12, plus t plus t plus 9t. That's 9, 10, 11t is equal to negative 10. And if I were to rearrange this, I would get 11t is equal to 22, and t is equal to 2. It is always nice when we get a nice round number. We can go and plug it back into our equation. I'll plug it back into here. So 2 plus t, 2 plus 2 is 4. Y is equal to negative 1 minus t, negative 1 minus 2, which is negative 3. And here we get 3 plus 3 times 2. 3 times 2 is 6, plus 3, it is 9. So our foot of the normal, is at point 4, negative 3, and 9, and that's the point where in which the line, that equation of the line that we came up using the normal, touches the plane. Once we have this, we can find the shortest distance. Let's assume that we didn't know the equation for the shortest distance. then all we would need is the vector QP and then its magnitude, because that's going to be the shortest possible distance. So vector QP is going to equal to, we're going to take the components of P, which are 4, -3, 9. We just came up with that, and subtract them by components of, or coordinates of point Q, which are 2, -1, and 3. Once we do this, we will get 4 minus 2 is 2, -3 plus 1 is -2, and 9 minus 3 is 6. Now the shortest distance is going to be the magnitude of our vector here, and that's going to be the root of x component squared plus the y component squared plus the z component squared. That's going to be 4 plus 4 plus 36, the root of it, and that's root 44. This can be broken down into root 4 times root 11, which is equal to root, or 2 root 11, and that is going to be our shortest distance from point Q to the plane. And I forgot to write my units here, so I will include that as well. You could have also, for the shortest distance, just used the equation, and our equation would also give us the exact same answer here. For part B of the question, we have the same situation. We got a plane. I'm going to call this plane 1. And we have our point Q, which is 1, 0, -2 in terms of its coordinates. We need to find the equation of the line here that connects Q and P. And for that, we need this direction here. To find the direction, we will need the normal to this plane over here, and unfortunately our plane is given to us in vector form. So this is vector B and vector C, so we need to find the normal vector to that, which is the cross product of the two. So I, J, K. And my B vector's components are -3, 1, and -2. And my C are 1, -1, and 1. To find the cross product for the x components, it's 1 times 1 minus -2 times -1 minus unit vector j, and -3 times 1 minus 1 times -2 minus the unit vector k, and -3 times -1, which is 3, minus 1 times 1, which is 1. And by doing this, we will get 1 minus 2 is -1. -3 plus 2 is -1 times -1 for the negative unit vector j. We will get +1, and 3 minus 1 is 2. Once we have the normal, we're actually going to find the equation of the plane in Cartesian form as well. It is going to definitely help us. So this is the A value, this is the B value, and this is the C value. So we got A times X. I'm going to use, actually I'll write it out first. So AX plus BY plus CZ minus D is equal to 0. A value is -1. My x value from up here is 1, plus b value is 1. Y value from here is -1, plus c value is 2. And my z value from up there is 1, minus d is equal to 0. So I get -1 minus 1 plus 2 minus d is equal to 0. And I get d is equal to 0, which is pretty nice. That means that our equation for the line is going to be -1x plus b times y, which is just y, plus c, which is 2, z is equal to 0. So that's our Cartesian equation there. Now going back for the equation of the line here that connects Q and P, this equation will have a point 1, 0, negative 2 that's coming from the point Q over here, and it's got a direction vector which is normal to the plane. That's this one over here. So I'm going to use parameter t and components negative 1, 1, and 2. It is nice to write these in parametric form as well. So this is going to be x is equal to 1 plus negative 1 times t, that's just minus t. Y is equal to 0 plus t times 1, that's t. And z is equal to negative 2 plus t times 2, which is 2t. Now to find the foot of the vector, I'm going to plug in these this x value into here, the y value into here, and the z value into here, and solve for t. And that will give me the scaling factor from point Q of how far it is in that direction vector where our point P meets the plane. So I get negative 1 times the x, which is 1 minus t, plus y, which is t, plus 2 times z, which is negative 2 plus 2t, is equal to 0. That's negative 1 plus t plus, well, minus 4 plus 4t is equal to 0. That we get that by expanding the top line. And we get negative 1, negative 4, which add up to negative 5, plus t plus 4t, that's 6t is equal to 0, and that means that 6t is equal to 5, or t is equal to 5 over 6. This is kind of sad because we don't have a nice round t value, but that's okay. We are going to go back here and plug it into our parametric equation to find the coordinates of point P. Our x value is going to be 1 minus 5 over 6. That's 1 over 6. Our y value is going to equal to t, which is just 5 over 6. And our z value is going to be negative 2 plus 2 times 5 over 6. 2 times 5 over 6 is 10 over 6. And if we get a common denominator of 6, we will get negative 2 over 6 or negative 1 over 3 as our z coordinates. And now that we have the coordinates, we know that the foot of perpendicular is going to be at points, or at point 1 over 6, 5 over 6, and negative 1 over 3. And this is the answer to the first part of the question. Since we have this equation over here, we can go ahead and use this equation to find the shortest distance to the line, but I am going to use the other method, which is just finding vector QP and finding its magnitude. And you can use this as well just to check your answer using the equation, but I want to show that both methods work perfectly fine. So we need vector QP here, so I'm going to write it there, and I'm going to use points P, 1 over 6, 5 over 6, and negative 1 over 3, and subtract these by the coordinates of point Q, which are 1, 0, and negative 2. Now I'm going to shift everything up so that we have a little bit more space. We got 1 over 6. Actually, I'll write this maybe in a little bit more more complete so that you can see what I'm doing. 1 over 6 minus, I'm going to get a common denominator here of 6. 5 over 6 minus 0 is just 5 over 6, which is just beautiful. We don't need to do anything to it. And for the next one is negative 1 over 3. Negative times a negative makes a positive. I'm going to get a common denominator of 3 and multiply 2 by 3 to get 6. And I will end up getting 1 over 6 minus 6 over 6 is negative 5 over 6. This is 5 over 6. And this one is 5 over 3. The shortest distance now is going to equal to the magnitude of QP, and that's going to be the root of my x component squared plus the y component squared plus the z component squared. This is going to be root. I am going to get 25 over 36 plus 25 over 36 plus 9, 25 over 9 here. I'm going to get a common denominator of 36. So we're going to have 36 plus 36. We get 25, 25, and we need to multiply the other one by 4 to get 100. And we'll end up getting root of 150 over root of 36. This can be simplified. I'll write it like this first, root 150 over root 36. Root 150 is same as root 25 times 6, so that's this one over here, and root 36 in the denominator is just 6, and this becomes 5 root 6 over 6 as our units as our final answer for the shortest distance between these two, between point Q and this plane. For our second question here, we're told that here we got a point Q, which has coordinates points of 1, 2, and k being an unknown value, which lies on this plane over here. The first part of the question asks us to determine that value of k, and that's not too bad because we know that if point Q is on the plane, that means for x plus 2y minus 2z is equal to 8. The x value is 1, the y value is 2, the z value is k, and that's equal to 8. So 1 plus 4 minus 2k is equal to 8. We get negative 2k. I'll just write it out like this. 4 plus 1 is 5 is equal to 8. Negative 2k is equal to, subtract both sides by 5 to get 3, and k is equal to negative 3 over 2. And here we're dividing both sides by negative 2. So that is the answer to the first part of the question. For the second part of the question, we're told to determine the coordinates of point P such that QP is normal to the plane and that P is 3 units away from the plane. Let's see how we're going to start this one off. So let's draw it out. So we get a plane. Let's say this is our plane pi 1. And basically we are going to have a point Q on it, and we already have the coordinates to that one. And we are going to have point P here. We don't know its coordinates, we are trying to find that one, but we know that it's 3 units away from point Q. Well, we know the normal to our vector. Luckily, our equation is given to us in Cartesian form, so the components of the normal is going to be the coefficients of x, y, and z. Coefficient of x is 1, coefficient of y is 2, coefficient of z is -2. Well, that's very nice. Now we know in which direction the vector is actually going. And we can find out what the magnitude of the normal vector is. And instead of the magnitude, we can change it to a unit vector. And if we change this to a unit vector, it will have a magnitude of 1. If we know the direction and its magnitude, then we can multiply that magnitude by 3, and we can figure out what per point P is. So let's find the magnitude of vector n first. So the magnitude is going to be the square root of its x component squared plus y component squared plus the z component squared. And that's going to be root of 1 plus 4 plus 4. And that's going to be 4 plus 4 is 8, and that's 9. Oh, and that will give us a nice round value of 3. Once we have this, we can find the unit vector, n. Actually, I'll write it with a hat, and that's going to equal to vector n over its magnitude. That's 1 over 3 times the vector, which is 1, 2, -2. And we can rewrite this as 1 over 3, 2 over 3, and -2 over 3. Now we want to figure out vector QP and use the idea that 3 times the unit vector n is equal to QP. So first of all, QP is going to be the coordinate points for point P. Those are x, y, and z. And we're going to subtract them by coordinates of point Q, which are 1, 2, and k. This is also going to equal to 3 multiplied by the unit vector n, or the normal, because we know the normal is going in the same direction. We know that its unit vector will have magnitude of 1, so if we multiply that by 3, we will reach from Q to point P. So I will rewrite this, or I'll just write it as it's equal to 3 multiplied by the unit vector n. I'll write it like this. And I'm going to shift everything up, and we're going to continue to write our equations and derive the value of x, y, and z for point P. So we are going to have x minus 1, y minus 2, and z minus k, which we found to be -3 over 2, is going to equal to 3 multiplied by the unit vector n, which is 1 over 3, 2 over 3, and -2 over 3. Here we will have, I'm just going to simplify everything before I move on. This is going to be z plus 3 over 2. That's my negative, and negative make it positive. And on this side, 3 times 1 over 3 is just 1. 3 times 2 over 3 is 2, and 3 times -2 over 3 is -2. This is nice and convenient. Now what we can do is we are going to use the x, y, and the z values, and we are going to find the value for our x, y, and z. So for the first one, x minus 1 is equal to 1. That means x is equal to 1 plus 1, adding 1 to both sides. That will give me x is equal to 2. For the purple, we got y minus 2 is equal to 2. I'm going to add 2 to both sides, and I'm going to get y is equal to 4. And for z, I will do that on, actually, I still have a little bit of space here. Z plus 3 over 2 is equal to -2. I'm going to subtract 3 over 2 from both sides. So I will get negative 4 over 2 minus 3 over 2, and that will end up giving me negative 7 over 2 for my z value. And therefore, the coordinates of point P are 2 for x, 4 for y, and negative 7 over 2 for z. Note that you can also check your answer as well. You can just find QP based on this equation. Just plug in x, y, and z, and then find the magnitude, and you should get a value of 3, meaning that point P is 3 units away from point Q. I hope that this video gave you some practice for the shortest distance between a point and a plane. You can notice that the questions are getting a little bit more challenging, but do know that we are getting into the more challenging parts, and planes are much more challenging than lines, and there's just a lot more concepts to them. So I hope with enough practice you'll get much more comfortable doing them. And again, practice here is key, and knowing your fundamentals, going back to the first lesson of plane and the second lesson of plane, and kind of really making sure that you understand them, using GeoGebra as a tool to kind of learn how three-dimensional planes look like will definitely help you with this. So practice, practice, and you will get better. Thank you for watching.